service described is a three-phase delta service. In a delta service, the three phases are connected in a closed loop, a triangle if you will, with each phase connected to the other two. This configuration results in a specific voltage relationship between the phases. Typically, you would find 208 volts between any two phases in a 208-volt delta system. The 120 volts from each phase to neutral, as mentioned, is characteristic of this type of system. The description of the voltage readings, specifically 208 volts from one phase to ground and 120 volts from the other two phases to ground, aligns with the expected behavior of a delta service. The term stinger leg refers to a specific configuration within the delta service. In a typical delta setup, one phase, often referred to as the stinger leg, is not connected to neutral. This leg can be connected to the midpoint of one of the transformer windings to derive a neutral point, but it's not inherently grounded like the other two phases in some configurations. When the voltage drops below 160 volts on line readings during peak load, this indicates a significant voltage sag. In a delta service, the nominal voltage between phases is 208 volts, and voltage drops can occur due to increased demand in the system. This can lead to equipment malfunction, particularly for devices designed to operate within a specific voltage range. The compressor failures described are a direct consequence of undervoltage. Where equipment designed for 230 volts is supplied with only 160 volts, it can lead to overheating and premature failure. Voltage-sensitive equipment relies on consistent voltage levels to operate efficiently and safely. Undervoltage can cause motors to draw excessive current, leading to overheating and damage to internal components. The issues mentioned, including the delta service configuration and the omission of crucial control components, highlight the importance of proper system design and maintenance. A delta service, while functional, may not be the ideal choice for all applications, particularly when voltage stability is critical. Additionally, cutting corners on control systems, such as omitting chill water bypass valves, can exacerbate problems during periods of high demand. A chiller bypass valve helps maintain flow through the chiller when the load is reduced. Without a bypass valve, the flow rate through the chiller can drop too low, leading to freezing and damage. The combination of an undersized chiller and lack of control equipment can result in a cascading series of failures, as described. Regarding the electrical service itself, it is important to understand the different types of three-phase systems. Firstly, there's the delta configuration, which, as discussed, involves a closed loop of three phases. Secondly, there's the Y configuration, where three phases are connected to a common neutral point, forming a Y shape. The voltage characteristics of these two systems differ. In a Y system, the voltage from each phase to neutral is typically the same, and the voltage between any two phases is equal to the phase to neutral voltage multiplied by the square root of 3, which is approximately 1.732. For instance, a 480/277 volt Y system has 480 volts between phases and 277 volts from each phase to neutral. The delta system, on the other hand, can have different voltage relationships depending on whether it's a center tap delta or a corner grounded delta. A center tap delta, also known as a higher leg delta, has one phase that is center tapped, creating a neutral point. This results in one phase having a higher voltage to ground than the other two phases, typically around 208 volts in a 240 volt system. The other two phases will have 120 volts to ground. In a corner grounded delta, one of the phase conductors is grounded, which means that the voltage from that phase to ground is 0 volts, and the voltage from the other two phases to ground is equal to the phase-to-phase voltage. When troubleshooting voltage problems in a three-phase system, it's important to check the voltage between all phases and between each phase and neutral or ground. Unequal phase voltages can indicate an unbalanced load, a faulty transformer, or a wiring problem. An unbalanced load occurs when the amount of current drawn by each phase is different. This can be caused by uneven distribution of single-phase loads across the three phases. An unbalanced load can lead to overheating of the transformer and conductors, as well as voltage imbalances. A faulty transformer can also cause voltage imbalances. Transformers are designed to provide a specific voltage ratio between the primary and secondary windings. If a transformer winding is damaged or shorted, it can affect the voltage output. Wiring problems, such as loose connections or damaged conductors, can also cause voltage imbalances. Loose connections can create resistance in the circuit, which can cause voltage drops. Damaged conductors can reduce the current carrying capacity of the circuit, which can also lead to voltage drops. It's also important to consider the voltage drop in the conductors due to the load current. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. The longer the conductor and the higher the current, the greater the voltage drop. The National Electrical Code, NEC, provides guidelines for calculating voltage drop in conductors. The NEC recommends that the voltage drop in branch circuit should not exceed 3%, and the voltage drop in feeder should not exceed 5%. To minimize voltage drop, it's important to use conductors of sufficient size and to keep the conductor runs as short as possible. In the case of the city hall's power problems, it's likely that the voltage drops during peak load were exacerbated by a combination of factors, including the delta service, the unbalanced load, and the undersized conductors. The fact that the chillers were designed to operate on 230 volts, but were being supplied with only 160 volts, suggests that the voltage drop was significant. This highlights the importance of carefully considering the voltage requirements of equipment when designing an electrical system. It's also important to consider the future load growth when sizing conductors and transformers. As the load increases, the voltage drop will also increase. Therefore, it's important to select conductors and transformers that are capable of handling the expected future load. The issue with the chillers highlights the importance of using equipment that is compatible with the available voltage. Installing 230 volt equipment in a 208 volt system can lead to problems, especially during peak load. It's also important to ensure that the equipment is properly protected from overvoltage and undervoltage conditions. Overvoltage can damage sensitive electronic components, while undervoltage can cause motors to overheat and fail. Voltage monitoring devices can be installed to detect overvoltage and undervoltage conditions and to take corrective action, such as shutting down equipment or switching to a backup power source. In addition to voltage, it's also important to consider the frequency of the power supply. In the United States, the standard frequency is 60 Hz. However, in some other countries, the standard frequency is 50 Hz. Equipment designed to operate at one frequency may not operate correctly at another frequency. For example, a motor designed to operate at 60 Hz may overheat and fail if it's operated at 50 Hz. It's also important to consider the power quality of the power supply. Power quality refers to the characteristics of the voltage and current waveforms. Poor power quality can be caused by harmonics, voltage sags, voltage swells, and transient voltages. Harmonics are distortions of the voltage and current waveforms that can be caused by nonlinear loads, such as electronic ballast and variable frequency drives. Harmonics can cause overheating of transformers and conductors, as well as interference with sensitive electronic equipment. Voltage sags are temporary reductions in voltage that can be caused by large loads starting up or by faults in the power system. Voltage swells are temporary increases in voltage that can be caused by lightning strikes or by switching operations in the power system. Transient voltages are short-duration high-voltage spikes that can be caused by lightning strikes or by switching operations in the power system. Poor power quality can damage sensitive electronic equipment and can cause malfunctions. Power quality monitoring devices can be installed to detect power quality problems and to take corrective action, such as installing harmonic filters or surge suppressors. In summary, the power problems described highlight the importance of proper electrical system design, maintenance, and operation. It's important to carefully consider the voltage requirements of equipment, to use conductors and transformers of sufficient size to balance the load across the phases, and to protect equipment from overvoltage, undervoltage, and power quality problems. The National Electrical Code, NEC, provides guidance on these issues and should be consulted when designing and installing electrical systems. Specifically, Article 220 covers branch circuit, feeder, and service calculations. Article 250 covers grounding and bonding. Article 300 covers wiring methods. Article 310 covers conductors for general wiring. Article 430 covers motors, motor circuits, and controllers. Article 450 covers transformers and transformer volts. Article 500 through 516 covers hazardous locations. Article 600 covers electric signs and outline lighting. Article 620 covers elevators, dumbwaiters, escalators, moving walks, platform lifts, and stairway chairlifts. Article 690 covers solar photovoltaic systems. Finally, Article 700 through 702 covers emergency systems, legally required standby systems, and optional standby systems. These are just a few examples of the articles in the NEC that are relevant to electrical system design and installation. It's important to consult the NEC for specific requirements and to ensure that the electrical system is safe and compliant. Understanding the type of three-phase system, whether it's delta or Y, is crucial for proper troubleshooting and maintenance. Each system has its unique voltage characteristics and grounding requirements. A delta system, with its potential for high lag in different phase to ground voltages, requires careful attention to detail. A Y system, with its balanced phase to neutral voltages, simplifies some aspects of system design but still requires proper grounding and load balancing. Consulting with qualified electrical professionals is essential to ensure that the electrical system is properly designed, installed, and maintained. Electrical systems are complex and potentially dangerous. It's important to have a thorough understanding of the principles and practices involved in electrical work. Regular inspections and maintenance can help prevent problems and ensure that the electrical system is operating safely and efficiently. The information provided is intended for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before performing any electrical work.